and feedback.
Great, thank you. You probably can't see it, but I have on my new ESIP shirt today, which I really like the new ones. We're big fans of ESIP at Alumni 4. So my background, I have a computer science background. I don't come from a scientist background. I don't come from disaster response. So I come more from the technology side of things. And I've been involved in I should say like geospatial, data processing for over 24 or 5 years, something like that. Worked with NASA and NOAA before, and I've been at Element for a really long time, since almost the very beginning. Today, I'm going to talk to you about reliability in AI, and this is showing kind of our current thinking on a lot of it, and a lot of it is just my thinking as well. This is something that like AI is so new that we want to understand how we can use it, and we want to understand where how it can help solve our problems, but also deal with the different challenges in it. And so it's like a very good timing for me to present this and kind of show what we're thinking about. So specifically, what are we going to talk about today? I'm going to show you some of the different AI solutions that we've been working on, kind of give you some context of where we are with that. I want to talk about how they work too. Something that's kind of a pet peeve of mine is, hearing about different solutions and then not seeing anything, kind of hearing like a hand wavy, like without understanding, like really, how does it work? How do you get there? Uh, I do have a lot of different things I'm going to go over, some of which I won't have time to get into, but I'm happy to have like other conversations outside of this too. So I'll be showing some of the past work. And then the meat of this is really AI concerns, challenges, and things. We've been doing user interviews, so we have real user feedback and concerns that they have, and then different approaches that we've been thinking about for reliability, transparency, and trust. And we have a small group today, so I think it's fine we just interrupt me with questions as I'm going. Uh, I like to start off with this slide. Every geospatial project begins with a quest for answers, that we have problems and really like we're asking a question, and sort of disaster themed questions here. Like examples that you might ask is, show me all of the urban rural interfaces with high fuel load risk, where you're understanding like where is there a potential chance for fire, and in particularly critical areas. Or what about infrastructure? You'd want to know which things like bridges are potentially problematic, or finding areas that potentially have a likelihood of a landslide, and then other factors that might contribute to that, like being burned recently, or even finding things like we're in the middle of identifying where can we put resources, like show me accessible helipads near an area that can be supported. I don't know about you, but when I want to understand geospatial data and get going on it, I always feel like there are way more hurdles than I want. It often feels like that I am running an obstacle course. I am searching an agency website and sort of navigating it, and I'll eventually find like, this looks like the data that will be useful for what I need. But then it turns out like, oh, this is the different area. It's only like from 3 different months, 10 years ago, and this isn't actually what I need. So I think when we've been talking to people, like I went around to AGU back in December asking people, what was it like, what are their challenges finding and using data. And I think this picture is a good representation of the response that I got, and that I kind of have like a newfound respect for scientists and researchers, and kind of the heroic ends that they have to go to find and use and like extract information out of data. And so what we're all wondering is, we have questions, and hey, LLMs are here and they can answer questions. Can it answer my questions? And so that's kind of like the crux of where we are right now, that we're talking about different capabilities that are there. And we've been wondering that too, and have been working for the last couple of years, experimenting and building solutions using our existing knowledge. And so we built, this is an example of one demo that we built, where we've taken a bunch of information, satellite imagery across Massachusetts that's pretty high resolution, and chunked it up using a vision model and be able to pull out vector embeddings for it. And we can build a natural language interface where you can say, show me new construction within 5 kilometers of the Quabbin Reservoir. And when we build things like this, we have to be able to understand what are the different parts that a user is asking about. So one of the techniques we came up with, to help do this is natural language geocoding. This is where we can take natural language phrases that describe a place on the earth that we might want to ask about and be able to convert that into a real polygon. The way this works is that we aren't just sending this directly to an LLM and asking it to give us a polygon. We're actually asking the LLM to parse apart what the user's asking for, and then that component, like parsed version, that tree that they're describing, we then process that to generate a spatial area. And this works surprisingly well. We can do complicated descriptions of things like within a few miles of Salt Lake City, West Valley City, and Mill Creek, except for the airport, and generate a polygon that represents that area. Back in December, when I was at AGU, I presented on a technique kind of building on some of these where we can take questions now that are asking about change. And this looks similar to what I showed before. We were asking about new construction. The way that other demo worked was it just the vision model was able to sort of ascertain semantically when it looked at an image, does this look like new construction or not? With this new approach, what we're doing is we're actually looking at images over time and being able to understand the difference in images and whether one contains more trees or semantically is different than the other. And so this is a graph kind of showing a few areas where we've graphed them out between 2018 and 2021. The lines that are in the same spot on the Earth are connected. So for all of these areas, the relationship with forest is stronger in 2018, or actually, like I have a little dash thing that's over my screen that makes it hard to read. That's better. 2018, these areas are more closely related to forest than 2021. And at the same time, for some of them, like these top 4 areas here, the relationship with houses increased. And if we go look at the images for those 4, 2018 to 2021, you can see they're very semantically, these are forests, and over time the forests were replaced and it's been replaced with housing. So using these kinds of approaches, we can be able to do change detection by looking at like what's changed, by actually like having the vision model tell us what's there. And this is an approach that scales really well. We basically analyze the data ahead of time and it can go in a database and we can find what's changed using something as simple as a select statement in order to do it. So this works across like a huge area, a huge amount of times. So we've been building towards this idea of what I'm calling a natural language geospatial computer, where we can take in questions from people in a UI and then pass that to a broker or a set of LLM agents that we use the AI to understand what they're asking about, and then be able to ground those responses using data that we've taken and indexed into things like knowledge graphs and vector databases in order to provide answers so that people can ask questions and get an answer back. And we've started to do that with NOAA. NOAA's been working for years, working on a system where they're tracking data that's been ingested into the cloud, and they are storing it inside of a knowledge graph or multiple knowledge graphs called a knowledge mesh. I'm not the expert on this particular area, but this is from a presentation that Ryan Berkheimer gave earlier this week, actually, where he was going over these approaches. And what we proposed was a system where we could take advantage of all of this data that they're storing inside their knowledge graph and be able to answer questions. So this is a diagram that looks very similar to the one that I showed before, but we're targeting personas like environmental policymakers, climate scientists, and marine scientists so that they can ask natural language questions We can use the knowledge graph to determine and identify particularly like what they're looking for. So if someone mentions pollution, we can link that to specific variables using a knowledge graph, and then variables connected to data sets and particular data files, and then go ahead and process that, extract that data, process it, and provide an answer back. So all of this sounds great, right? Like we're working towards being able to do that, but there are challenges, right? People have concerns about using AI, like justifiable ones. We know hallucinations are a problem that, potential, like for how LLMs work, generating text that is similar to text they've seen before is like almost the definition of a hallucination. And the way that they work is almost a hallucination in and of itself. And you can ask it to generate you a quote. And this is something that LMs are bad at. If you ask them to tell you something that they've seen before, like a particular quote from a book or something, it'll most likely be incorrect. They also kind of act like a black box. You can ask a question and get an answer, but it's hard to determine where did that come from. And we're worried about things like bias as well. When models are trained, they're trained on like what data that we had. And if the data isn't representative of all users, all places on the earth, uh, it can encode bias into the model itself. And so when we ask about things that the model hasn't seen before, it may be more likely to not be able to handle that kind of a situation. And also, I'm wondering, is chat the right interface? Like language is a fundamental part of how humans communicate, but do we really want a chatbot in order to conduct science or ask questions? And so we're working and thinking about that, and it's probably going to be more something along the lines of chat combined with other, with traditional UI elements. Additionally, like these models are non-deterministic, as in they work essentially in a way where it's not going to always be repeatable. And so you can ask the same question and you can get different answers, and which is kind of opposed to the idea of reliability and being able to do science where we can reproduce results. And so all of these concerns really are almost anti-science in a way, right? Like not being able to understand how it works, not being reliable, is problematic. And so let's talk about disaster response, mitigation, and recovery, because this adds kind of a new wrinkle to what we're thinking about. I really like this. I should say, I don't come from a background of disaster response. I mentioned that at the beginning. Um, Element 84 has worked in, disaster resilience, and we have a few different people who are in that area, not including myself. But I found this image online from the All Hazards Consortium, and I really like the way that it represents all of the different things that you have to worry about in a disaster response situation, where you have to understand things like the ability for repair crews to get to a particular area, whether it's going to be secure or not, food and water for people, and damage assessment. Even things like as simple as finding parking can be a problem. I had a conversation with someone who supports forest fires, and I was talking to them about a UI chat interfaces and whether it would even make sense in a situation like that. And I was surprised that they said that they thought it would, based on you know everybody's not a GIS specialist, and being able to ask in plain language for things that you need would be really helpful. And an example they had was, I need to be able to park, equipment, fire trucks, things like that. And where can I park it? Where is going to be safe for us to put this? Where is it near a water source? Is the grading stable? Is it like actually a clear area? And so it ends up being a geospatial problem, being able to find that. At the same time, it's also like potentially life threatening, and if it's going to be safe or not. So, and then there's operational challenges you have to worry about, right? Information uncertainty, coordination complexity, resource constraints. You're managing limited supplies, limited volunteers and equipment. Then you have this time pressure where you're balancing speed with thoroughness in critical decisions. And then there's scale dynamics in terms of adapting response as disasters escalate or evolve unexpectedly. And then you have to integrate data from multiple sources. And then there's the human factors here where you're, maybe working for a long time and then, too many decisions evolves into decision fatigue, psychological stress, information overload. You're handling misinformation where there's rumors and things like and keeping people informed. And then there's organizational boundaries where you're working within different groups and who's in charge of who and whether, you can make a decision that will, you know, have things happen. And then working in different, groups in the communities, you have to be aware of their cultural sensitivities and things that they're going to care about. One of the examples in my research when I was looking through disaster response that I found really insightful was just focusing on data usage and what can go wrong there. There's a lot of different problems that can happen in terms of data can be out of date, or you could be looking at data and not understanding the particular resolution. Like if you're looking at data that's generated once a day, and you're trying to figure out the differences between morning and the afternoon, you won't be able to actually get an accurate answer because of that. And similarly for spatial, if you're asking for things that are too close together and it's not within the spatial resolution, you won't get accurate answers either. Data can be unverified or not production ready or unavailable even. So I found through ESIP's disaster cluster on their website, I really like this idea of the operational readiness levels, which were developed through a series of different groups. And I really like what it's doing, which is basically ahead of time in preparation for being able to be used in a disaster scenario. It's understanding where can this data be used safely? Like at your top level, you know that this is secure and available data. It's got the complete metadata like the one I listed before. It's verified and tested. And also, if you're asking questions in the chat, I might not see those, so feel free to just interrupt me. I'm going through things quickly. And so I like this as a way to deal with a very real problem where it's easy for humans to make mistakes and do the wrong thing, and especially with time sensitive. And so let's go back to AI solutions and our approach. So as an overview of what we're doing is as we bring in AI to solve these problems, we want to be really thoughtful about whether it's appropriate or not, whether it's the best fit for it, and also not try to be absolutist about whether it's definitely going to be there useful or it's always going to be that there's nuance involved. We also trying to be user driven in terms of all of this that we're doing. We are bringing in users early. We're doing user interviews. We're involving them throughout the entire process, and we are designing for reliability. We're testing for reliability. I'll get into specifically like what we're doing and different approaches. And then involved in all of this is iteration, right? As we're developing these solutions, as the industry is, there's going to be a series of lessons learned, and it's going to take multiple tries in order for it to get to the most stable, complete solution. So from a user's point of view, there's a metaphor that I like to use that I call the hill. And we see that there are users and problems, and that there's technology out there that you want to use to help solve it. And the hill represents, in the metaphorical space, the effort you have to expend in order to connect to the two, but it also represents a lack of knowledge. If you're familiar with technology, you might not be able to see and understand all of the different users' problems. And if you're coming from the user problem space, you may be particularly focused in that domain in small, iterative fixes. So we have to think about like what side do we actually start from if we're going to look for a solution. I, from a technology background, a lot of times come from a technology side where I have a vague idea is what your users are out there and what problems they want to solve. And so I know what's possible. I see like a big potential, and I have this, excitement about being able to solve problems. And there's this gee whiz factor. And I think a lot of the AI solutions out there are kind of coming from this. Uh, from the user's side, we can understand the problem. We know the user. We have empathy for their problems and want to solve it. And that makes our work meaningful. Uh, So let's say we start from the technology side. We can know it and understand it, and we go off in search of users, use cases, and problems where it can help. But we tend to grasp at straws. We're thinking of like, what's the best way to do this? And we can create a demo. Like I'm very familiar with this idea. And the problem with this approach is a lot of times that we end up solving for the imaginary user. The imaginary user is a person that's 100% satisfied, and the demo perfectly meets their needs. But what the problem here is that we are building something that's incomplete. We don't really understand this, the person that we're building this for. We could be solving the complete wrong problem, and we're missing all sorts of things like norms and cultures and what the particular environment is that they're operating within and whether the solution will work there or not. And so what we do to combat that is we have a geospatial discovery design process that we use. And this is like exactly what we're doing on our NOAA project and other AI projects that we're working on, where we do things like hold workshops, we do user interviews where we talk to them. And I found this is really fascinating to go and hear from users on and different concerns they have about this approach and where their actual challenges are. Something that I found kind of surprising, but I don't know if I should, is when I'm asking people about particular problems in geospatial, they say things like, it's really hard to find the data. I can't search it on the website, and I have to download really big files. And these are problems that I remember hearing about, 15 years ago that we've been working on. And so there's solutions that people have been doing, but it doesn't seem like we're there yet. And so we follow this process where we do, end up building diagrams and wireframes, and then we show those to users to get feedback and iterate there. Eventually, we're doing user testing and building designs. If we look at the geospatial analysis workflow, it might be some steps like this, where we're defining a problem. We're then acquiring the data that we want and pre-processing it. We're conducting spatial analysis and modeling, building visualizations and interpreting the results, and then like evaluating those results. Do they make sense or not? And then at the end of this whole thing, we're communicating it out. We write our paper, we publish our report, and we get feedback. And I think concern that I hear from users when we talk about this is that we're solving for this whole thing. And if we were to just say this is an AI thing where we're going to let it define the problem and go through all these steps and then post a paper, this would be a robot researcher. This is what the users do not want. And this is also kind of what we're afraid of as well in terms of does this even make sense or not? And this is not how we're approaching the problem either. Our philosophy is on augmentation, not replacement. And if we can think about it from the point of view of accountants, as an example, over time, different technologies have evolved to make this easier. If you're a character in a Charles Dickens story, you're doing all this manually and writing in a ledger book. But eventually, over time, like different technologies come along that make your job easier, right? Calculators and spreadsheets. But these aren't replacements for an accountant. They just help the accountant do their job. And we're thinking about AI is that in that way as well, that we're looking for more about assisting with individual steps at first, things that will really help core problems that they have, like finding the relevant data, being able to ask a question that understands and goes to the knowledge graph that is being developed. And if that makes it easier to find the data, then that's great. Things like being able to quickly do visualizations, extract or clean up data, anything where it's really going to impact users in terms of saving them time and getting to the point where they can do the real science, the real research to be able to really like answer the questions that they have. So let's talk about reliability. So I wanted to define that. And this is a kind of working definition that I'm going with. Consistency is one of them, right? We want to be able to ask a question and get the same answer every time. We care about accuracy and factuality in terms of, are the answers correct or not? It's not just the answer of, is the sky blue? No, we get that answer every time. We also want to get the right answer. We need robustness in terms of handling different phrases, handling unexpected inputs, being able to handle that gracefully. And we need it to be predictable. As users use these systems, they need to understand how it behaves and be able to learn that and have it be consistent with that over time. And then we also have to be able to handle uncertainty. If a user asks a question and we don't know or can't answer it, if they're asking for a level of granularity that doesn't match maybe the temporal resolution that we have available, we don't just fudge it and give them an answer anyway. We have to be able to say that we can't do that. There's kind of a thought technology that we've come up with for I think is one of the key things that will enablers for reliability, transparency, and trust, which is the concept of algorithms as graphs. And so when a user asks a question, what we want to be able to do is have the LLM interpret that question and translate that into something that will represent our understanding of what are they asking and what are the steps we need to do to get that answer. Uh, so if a user is asking what's the mean sea surface temperature in the Black Sea on June 1st, we would translate that into a graph that might look like something like this, where the first step here is doing geocoding, understanding where is that area on the Earth, Black Sea. We're going to take a variable of sea surface temperature that we've identified and filter our data to that, filter it then by temporally to the particular date that they're interested in, then compute the average and convert that finally into a unit that we can then display to the user. And what does an LLM do? We're give it the question and we actually tell it, generate JSON. And the JSON actually represents that algorithm. This JSON is based on a JSON schema, so it has to conform to that, which helps the LLM know what it needs to build. Each of these items here, like filter data array, are references to real tested versioned Python functions. We could have the LLM just generate Python, which is like one of the first ways that we tried it, but that was temporary. The problem with large language models, with the fact that they are non-deterministic, is if you give it the ability to generate anything in the world, the chances are there's like more opportunity for it to make a mistake. If we limit it somehow and say like, no, you can only generate things that conform to this JSON schema, you have to choose from specific functions that we know that are available, we are making it less likely to generate something that we don't expect. And so let's show how this ties into the user. So this kind of shows a typical flow where user is going to ask a question like, what's the average sea surface temperature in the Chesapeake Bay in each summer over the last 5 years? We send that to a set of LLM agents. And the LLM's agents' job are to translate basically from human language into computer language. And one of the first steps is to translate that into a search that goes against a knowledge graph for to be able to find what are the data sets related to what the user is asking about. Then we're able to use another LLM agent to generate that algorithm representation. And we take that and we reflect that back to the user. So when we're doing that, we're showing the user our understanding. When they ask a question, here's what we understood your question to be. Here's the spot on the Earth that they're talking about. Here's the time range that we think you're, and then here's what we're doing in order to answer your question. And the user has the opportunity at that point to be able to clarify, to understand like, okay, I see what you're doing. This is either, yes, that's what I wanted, or no, it's not. They can change their mind and ask for something else. And after we run it, we need to be able to explain to the user what happened. As we're executing this algorithmic representation, we can track that. We can track the different steps that it went through. And so we're generating here is provenance. We know the provenance of the data sets because we've indexed that into our initial knowledge graph. And then as we're taking those data sets and we're performing different operations on it, we can track that and we can give the user an answer. And it's not just a blank answer of like, you wanted to know what the sea surface temperature is for this date. Here's the temperature. We can actually show it. What are all the steps we went through to get that answer? What is the data that this came from? Who generated that original data? What are the versions of the algorithms that we did on this, so that the user has this ability to be able to see how was everything produced, and this gives the user trust that we're doing the right things. It lets them verify themselves. They can reproduce it if they want to, or be able to give feedback and say, I want you to do something different, and run it again in a different way. Let's talk about reliability. A lot of the things that I've been talking about so far have been focused on reliability tangentially, uh, but that there's additional details here that I can expand on. So one of the things that you'll notice here is where LLMs integrate in is kind of scoped in a specific area. Because LLMs have this non-deterministic nature, uh, we don't want to rely on our entire system to be based on that. We want to scope that potential for hallucinations, for unreliability to a specific area. Everywhere outside of the use of the LLMs is normal, testable code. We know how to make that reliable. It is, you run it once, you can run it 5 times, it's going to produce the same answer. And if we zoom into the LLMs themselves, there's different things we can do to help improve the reliability there. One of the things we can do is automated testing. We've developed approaches where, as we're developing LLM agents, we can have automated tests where we test them with various inputs. We have a set of validations that we can run to check that, hey, they're producing the same output. And the way that the system is built, these are composable individual units that can be tested on their own safely. We know, I mentioned before, like you ask an LLM to give you a quote that someone said before, and that's a very easy way for it to hallucinate or something, right? In here, we're not asking for the LLM to just guess and figure out like what's the sea surface temperature and probably do it, or what's the name of a data set. We're not relying on the LLM to intrinsically know that. We're using the LLM to do this translation from a user question into a search of real, true, factual data, and it finds those and then uses that to build a further answer. So we're grounding an LLM in real facts here that we know and trust. Everything that the LLM produces in terms of a search on a knowledge graph, an algorithmic representation, or otherwise is something that we can validate. We can validate that the searches are searching real fields. We can check that the algorithm that gets generated makes sense, that as it's using and passing different inputs to these other pieces, that the types match, that we're not trying to calculate the average of bird names or something like that. And additionally, like I mentioned this before, we're constraining the output. We're telling the LLM exactly what we want out of it. We want you to generate this JSON that must conform to the schema. We can validate against that, but also that constraint really informs the LLM and helps it ensure that it's going to be reliable in terms of generating something that is going to match what we want. Additionally, these algorithms themselves can be captured. Like if we have a pre-known way that we want to, approach a particular kind of user problem, we can capture that. And Noah calls these process templates. I like the name or recipe, but those can be captured inside of your knowledge graph as well. And so for particular data sets connected to specific variables or particular kinds of problems, you can have that in the knowledge graph. And so part of what the LLM's job may be is just asking or figuring out, the user is asking for this kind of a solution. We have a pre-tested known recipe built that solves that, and we will just select that. And then we know from that point forward, that is something that we have versioned and tested, and the user will be familiar with how it works. That was a very whirlwind tour of everything. But we are definitely looking for feedback on concerns and reliability. We're going to be continuing to develop this. I would love to hear ideas. And if you're a user of this kind of data, we're doing user interviews. So we would love to have a half hour of your time. Please reach out and contact me. And, I'm happy to uh, answer any questions now on things. And I also have demos too that I can do if you want to see some examples of things.
Yeah, go ahead and do a demo. That'd be great, Jason.
Okay. So I'll just do a refresh here. So this is an example of our NOAA system. This is an early version of it. And this one is not yet using the algorithm approach, but we can ask a question here like, what kinds of questions can I ask? Right now, this is an LLM, uh, and it has access to a single sea surface temperature data set. It'll take a little bit here. All right. So what I really like with LLMs is you have this meta ability. You can ask about what you can ask about. So here it tells me what it knows about sea surface temperature and sea ice fraction, and it gives you some specific questions that you can do. So I'm going to ask about my README here. I've got some examples here. Which variables are available in the data set? This demo is not available online right now. So if you go to this URL, it won't actually work for you. So it tells us about our data set. We can ask about that. It contains 3 variables. We have our analyzed sea surface temperature, our CRS, and our sea ice fraction. And one of the cool things here is I can say, show me visually what these variables look like. Something that I haven't been showing here is if you see this output here, it has thoughts. Whenever we ask the LLM a question, we have it tell it, what are you thinking? And so it says like, oh, about the question you asked, it doesn't appear to require code, but I can reply, give it information. If we ask something that actually requires, looking at the data, we have more things that are output here. We have LLM thoughts about this saying we want to visualize this variable. We want to, this actually generates code. In this case, this is not yet, we're going to switch this to our algorithm approach. This is generating Python code. We go off and run that. It gives us an explanation of what our code is doing, creates 2 subplots using matplotlib and cartopy. And then it runs the code and gets output. And here we can visualize our data set. And it looks like, I think in this particular one, it's inverted, but we have sea ice fraction and our sea surface temperature. And now we can ask a specific question about sea surface temperature, like, can you draw a bar chart comparing the max sea surface temperature in the Chesapeake Bay, Delaware Bay, and San Pablo Bay for a particular month?
So that's thinking, Jason. I remember asking you. I think it was on Slack or somewhere. As this returns products, can they return geospatial services like web services or KML or something like that that we can put into other GIS visualization tools?
Yeah, definitely. I don't know if our current one would support that, but that's something we can definitely support where you can say, uh, after you preview it, give that to me, give me this area, in a CSV file or whatever else you want out of it. So as this is running, basically it's showing output for intermediate steps. And part of it is doing the geocoding for these different areas. And then at the end here, it gives us our bar chart and tells us the maximum sea surface temperature for these areas. So we can see here uh, Delaware Bay and San Pablo in June. It's a bit colder on the West Coast than the East Coast.
So just as easily, I guess you could tell it to give you the temperature in Fahrenheit or Kelvin or whatever, and it would do that? Or you'd have to
Sure,
build that
let's
in?
say that. Let's give that a try.
Fahrenheit would be good. What area, what group in NOAA are you working on with this?
Uh, I'm still learning the different NOAA acronyms. I think NESDIS is probably the right one to say.
Yeah. Hmm. Seems like it would be a good solution for NCEI and their customer interactions for climate data and climate information.
Mhm. And so this whole project is a prototype for NOAA. They're being very careful about um, putting AI in front of users, until it's been validated and checked. And so, right, this project is about determining the art of the possible.
Yeah. Yeah. And of course, as soon as you open it up to users, they're going to ask all sorts of questions that won't get answered correctly, and then they're going to get inundated with questions.
Yeah,
So,
yep.
like,
And
what
that's
kind of
why,
user support will they have?
yeah, this is taking a while, but the end result here, I'm sure, will be it in Fahrenheit.
Yeah, this is great. Want to open the floor to anybody else who has questions that's in the meeting here. I have several, but I'll wait till the end.
So I can see the chat. I'll let people know in the future. I'll try to publicize it if we're at a point where we want to open up the demo to people.
Hi, Jason. This is Tao from Oklahoma City State University. Yeah, thanks so much for your presentation. It's very impressive. And so I do have a question about the algorithm, the recipe. So is there some kind of algorithm that you developed the team by human being, or is it generated by AI?
What we give the AI is we tell it we have these tools available, or maybe not tools isn't the right word because that's overloaded with agents. We tell it, here's what the user wants. They asked for this specific phrasing. And we say, we have these capabilities available. We can download data sets. We can, if I go back to my diagram here, I might be able to show like the example again. This one, we have the ability to like do geocoding and filtering by area of interest or reducing. Like there's going to be other sorts of, and so what the LLM is doing is it's from this set of particular components that it has, it's going to compose that together into an algorithm to produce an answer. And that so this is on one hand, we could be completely opening it up into the LLM and saying, hey, just write Python, and you have the world's your oyster in terms of whatever libraries you want to use, and it could do anything, but that's less likely to be reliable to where we constrain it. On the other side is we tell the LLM, we know these 3 or 4 or 5, whatever algorithms that we've pre-developed and choose just from those. What we're trying to
Hmm.
find is like, where's the middle ground where we can have known working algorithms or recipes, but then also letting it handle things that it hasn't seen before, but doing it in a way where we can have some assurances that it'll work. If it's this simpler tree that's easier for us to validate after an LLM generates it, that it's going to work, that these types align in
Hmm.
in terms of producing what we want.
Okay. Yeah. So actually, Chen from East Tennessee State and I received the C grant from ESIP. And in that grant, we also use generative AI to automate the dashboard development. And
Mhm.
we take like Central Prussia flooding as a case study. And so we do have use the LLM as and as well as like train thought framework and to automate the data processing, data visualization. But from the data collection perspective, we try to use the generative AI or ChatGPT to automate the data collection process. However, we found it's kind of challenge because the different data sets, they may coming from different data sources, and they have a different spatial temporal resolution, and
Hmm.
they may rely on different kind of packages, and some of them may be because we just narrowed down to focus on the specific the region as well as the date. So we found it's kind of challenge to automate the whole process using AI tools. So how do you think of this?
I'm focusing in on just one of the particular things you mentioned, like having different resolutions and things like that, I think will be a challenge. I think all of this is challenging for users and is part of like when they talk about doing it themselves is part of the problem. And so what we've got to build is like a robust system that can handle data that's, has different resolutions, different CRSs, right? This data is in Fahrenheit, this data is in Celsius, and be able to recognize that and
Mhm.
map it. And so that can either be done by the people developing the data, right? It helps users and automation if uh, they're consistent. And I know like some of the problems people talk about is like you go to different uh, sites, even within the same agency for like weather stations or something, and then the formats of the files will be different. And then you have to know like in 2020 or the year 2000, the format changed in this way. You have to be able to
Yeah.
handle that. So I think if you iterate enough and build a robust enough system,
Hmm.
you can handle those sorts of problems. But it requires encountering those and being able to understand, like, yes, that's going to be a problem ahead of time. Um,
Yeah.
at a very minimum, you have to be able to recognize, at least when you're looking at the data, that it's in a format that you can use. And so that's part of like LLM reliability is being able to
Mhm.
when it's working with a piece of data, it can recognize, oh, this is outside of the scope of what I've been built to handle. And so it needs to like eject at that point or tell the user that it can't.
Yeah, yeah, I totally agree with you. During the presentation, you mentioned the more flexibility that we give to AI, and then I think that they may have more like errors or may have more misinformation or some. We need to, as a researcher, we need to spend more time to do the verification processes. So how do you define those kind of boundaries? Like what kind of task can totally give to AI and what kind of task we needs to be either better to just develop by our scientists.
Yeah. I think we're working towards them being able to do more multi-step, longer processes. But I think the good starting point is, hitting the things that will have the biggest benefit for users, which I think based on feedback is help me find the right data set and then let me look at it. It's like
Mm,
it seems to be like a common one, and then make it easy for me to get it.
mm,
If they can do those things and they're happy, like, okay, then I can take it from there. And if we can build a system that can do that at the beginning, I think that'll have a lot of benefit. And then you can build from there and being able to do more complicated things.
okay, yeah, thanks. Thank you so much.